In the specification sheet, check the anode angle and see which filament lens is being used so that you understand. With all due respect, these needs ultimately affect what you have. For example, if I am talking about dental, I am discussing something that doesn't require. I am not providing, for instance. No, I am providing something like that, just something big. I want, for example, what is reasonable to choose to have. No, I want something more dedicated, for example, a smaller field size with high resolution, and I can take several images. I want high cube loading, so I choose C. But if I'm talking about CT and high-end devices, I choose number B. Excuse me, doctors, is this point clear, or is there a problem? If there's something, please repeat it. And who controls these aspects? Is it the computer of the device? Because you mentioned that the X-ray tube comes with several anode angles. So is it controlled by the computer of the device or the operator working on it? No. The filament size can be different. You might get a short filament or a long filament. The tube angle is fixed. It comes as one. The change in filament size, Dr. Hani, is in the selection process from the beginning, and you should do the purchasing. You should look at the specification sheet. So today's lecture, if anyone is thinking of buying a device or something, you will find something called the tube rating chart and something called the cooling chart, as we will discuss them shortly and how important this is. You might buy an 8th row of detector CT, for example, and find that the device overheats. For example, it needs a cooling down period of about half an hour after each case, right? Surely you have seen devices like this that say the device is cooling. The whole idea is what? The whole idea is what I am talking about, and these options are put in place by companies to sell. In the end, they are selling you certain options. For instance, if you want to buy, they might say, have you heard of something called the tube power? How many megaheat units does the tube have? Is it 5 megaheat units or 8 megaheat units? For example, in some CT devices, it might be 3.5 megaheat units. This device, for instance, if you are doing a limb scan and performing lower limb angiography, it might not last the full 150 centimeters. If there is a long scan, you might find the device stopping because its heat capacity is low. So, I need a device with 5 megaheat units, or if it's a 64-slice device, I need 8 megaheat units. This way, my tube loading or power loading will be good enough to handle the high parameters. Doctor, yes, the technician selects the ceramic size to work with, or there is an option on the machine if he understands. If he understands and knows, he can choose from the devices available now. Most of them are accessible, for example. They are used and available to you. You have an example of a short filament that gives you a small focal spot, and there is a filament for a large focal spot. You can choose from this option and control whether you want high resolution or low resolution. All right, doctor. This point might be a bit confusing, but I hope I understand it correctly. It's like Dr. Hani was asking me about the questions regarding the actual focal spot size and the effective focal spot size. Of course, this will be, God willing, if the PowerPoint contains a lot of information on the topic. I mean, I don't read the text, but I try to convey all the information, God willing, as I speak, with clarifications. Here, for example, as we were discussing, if I need a different effective focal spot size, such as in mammography, macromammography, radiography, or fluoroscopy, you will find that the lower the resolution required, the larger your effective focal spot size will be. For example, there is fluoroscopy used for cardiac procedures that require a small field coverage, while in cases that involve intervention, a larger field coverage is needed. Therefore, for the machine and the modality being used, the field size varies according to what you see, such as 0.1, 0.3, 0.3, 0.6, 0.2, or whatever the available value is. It is very important to distinguish its movement in the problem used. I have a small one here, so I was able to reach a good result. But if I have something above my action, it gets bigger. Therefore, there can be an X-ray point here and another X-ray point there. So you find this area connected to two different points from different sources. This works normally in the area I was talking about, and you end up with a point of unsharpness or blurring effect, and you experience This is largely dependent on the area concerning the distance between the source and the distance between the subject itself. The closer the subject is to the source, the larger the penumbra area will be, and the greater the unsharpness will be. It is preferable for the subject to be further away. The closer your subject is to the source, as you can see here, the larger the area becomes. The unsharpness and blurring effect increase significantly. Therefore, it is preferable for the subject to be farther away. It is strong because it remains close to the image recipe. Here, this is also the blurring effect that occurs with the large spot size at the same distance from the object that is present. Please, go ahead.
We just said the O. The film car, a symbol of cinematic innovation and creativity, representing the evolution of storytelling, the film car, the film car, the film car, the film car. Then more of even more. Transfer from Catholic to another one. Small,
It's not the distance, Doctor. The actual focal spot size or the area that will be bombarded by the electrons will increase. For example, the distance remains the same. But the whole idea is that the area exposed to the beam of electrons will increase with the increase in filament length. Well, I furthermore want to say that before we get into this particular area of discussion, specifically related to focal spot size and its dimensions, when we were talking about this video earlier on, did you find anything here? What exactly is getting smaller? In the anode to cathode direction, the size of the focal spot size decreases in one direction. This means that the dimensions of the focal spot size are determined by two factors: the filament length and the focusing cup. We discussed the topic of the focusing cup last time and mentioned, let's assume this is basically the filament, and I have electrons essentially coming out from the filament here. Now, if there is indeed no focus, what could possibly happen? What's happening? What is the capacity of the electrons? What prevents these electrons from spreading out like this and hitting the anode in different places? I mean, what keeps all these electrons from being focused in the area of the focusing cup? Are there things that you can make or create using your own skills and resources? Consider the various possibilities that lie within your reach. For instance, you might be able to craft a beautiful piece of art, such as a painting or sculpture, using materials that you already have at home. Alternatively, you could try your hand at cooking a delicious meal from scratch, experimenting with different ingredients and recipes to create something truly. It remains useless for me. So, to focus the beam of electrons, what should be done? A large negative charge is applied to the focusing cup. A very high negative potential is used, and as the electrons exit, as you can see, this is the focusing cup. The electrons want to spread out. If you want to enlarge, they spread out. What happens? The negative charge focuses the beam, so the electrons will gather again. This is called the focusing cup. which I talked about last time. Of course, the focusing cup is connected to it. If the beam is high in this way, 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 if the beam is high in this way. These cases are similar to fluorography cases in particular if you want to deliver extremely strong pulses from the beam. Specifically, if you want to provide 2 pulses or continuous pulses, there is a specific frame rate you need to work with. You can give the X-ray beam an on and off state. I can achieve this effectively using what is called grid-controlled X-ray tubes. This is done by connecting a negative 4000 potential to the focusing cup precisely. All right, sometimes you might be, for example, like a fluorography technician. If you want to make your beam appear as if it is on-off in this mode, if you want to make your beam appear as if it is on-off in this mode, if you want to make your beam appear as if it is on-off in this mode, if you want to make your beam appear as if it is on-off in this mode, like one of the outputs, yes. Once, and then, for example, there is a frame or there is something between the first and the second, right? It seems continuous, but there is a difference between each image and the next, especially in cases of fluorography. There is indeed a difference, but it is a small difference. To achieve the strength of the X-ray or the strength of the X-ray beam that gives you this effect, what you do is connect the focusing cup to a high negative potential. So at minus 4000, what happens is that it creates more focus, but at the same time, it's like it's doing what? It turns on, then it stops, releases, and then goes back again. It's as if you have applied a very strong force that pushes the electrons out all at once, creating a high push for these electrons, which then interacts with the anode, resulting in a sudden output. But then it happens, and then it goes back again. You understand what I mean? For example, in the 100, you have a certain number of electrons, and there is a beam, as if there is a continuous beam from the X-ray. So there is a continuous beam of electrons. But in the case of negative 4000, no, you don't do that. You turn the on back because you have done a push or high push for the electron beam and produce the X-ray, and then there is another sequence or another pulse. What techniques do you use? Do you use cardio, for example? Anything important in fluoroscopy, such as if you are taking a sine view or continuous sine, or images in fluorographic sine, for instance. This is among the things or applications All right. This part is about the anode angle, the tube, and the filament size, and their relationship with each other and with the effective focal spot. I will include some questions in the quiz that I will send to you. These questions will test whether you understood the information regarding focal spot size and its relation to tube loading or its relation to resolution. So, after the lecture, if you review this material, it will help solidify your understanding. Just go back to it so that your understanding doesn't fade away. It will greatly benefit you in reinforcing this information. Okay, before I move on to the component, I want to explain the anode heat effect. To give you a better understanding, let me elaborate on the concept of the anode heat effect, which is crucial in this context. Furthermore, we have already agreed upon the fact that I have angulation, which plays a significant role. Is it present for the anode, right? Okay, if I assume that I have a certain point, this point, this is what happened in the interaction. The X-ray beam came out like this. So, what about the X-ray beam that comes out if we assume that I have this point where the interaction occurs? Let's call it point A, B, C, D, or E. Do you expect that from point A to point B, the X-ray intensity is the same as the X-ray intensity between point A and point C, and between point A and point D, and point A and point E? In other words, is the X-ray beam homogeneous, or is there a difference? Is there more difference at point P here? So, which point is higher and which is lower? P has a higher intensity than F, right? Why? Because there is attenuation occurring within the anode for these X-rays. Great. As a result, when the X-ray exits, part of it passes through the anode itself, causing specific attenuation for the low-energy X-ray photons. Consequently, you find that the intensity here at region F is lower than at P. The further you move towards the cathode, what happens? The intensity increases, so you find that the X-ray beam intensity at the cathode side or towards the cathode side is higher than the beam intensity. At the anode side, is that okay? Great. Very good. So if I come to a certain anode angle, if I reduce this anode angle, what happens is that the efficiency might change, and we need to consider the implications of this adjustment. Do you see the anode heel? What happened to this? What happened to this is called the anode heel effect. Come, let's see together. This is the X-ray beam coming from the anode, and this is the central axis for me. This is the direction of the cathode, and this is the direction of the anode, as we mentioned. As the doctor pointed out, there is a part that comes down here from the anode material itself, causing attenuation. The intensity, as we discussed in the last lecture, does not refer to the number. We are talking about the summation of the energy of all the photons present. This part was a bit confusing because one might say the number does not refer to the number, but it's as if you take the count and multiply it by the energy of each photon and sum it all up. That is the meaning of intensity. You will find here that the intensity is 70% at the anode, while here at the cathode it is 120%. Logically, if you are doing a scan, for example, of the abdomen or a specific area of the abdomen, there is a part in the upper abdomen and a part in the lower abdomen. Naturally, which part will be exposed to the cathode side and which part will be exposed to the anode side? The upper cathode side, which is the part with higher thickness. If we say upper and lower abdomen, I am talking about the abdomen, not the abdomen pelvis. So this part will be exposed to higher thickness at the cathode and lower thickness at the anode. Therefore, my angulation of the X-ray tube primarily relies on utilizing the anode heel effect to ensure that the image produced is homogeneous. If I do not take this variation or the angulation of the X-ray tube into account, it will give us a non-homogeneous image. Let's see. We will refer to it here as the anode heel effect, of course, because here is the shape of the beam. Here it explains to you what happens. This is the X-ray beam that comes out as a result of what is inside the anode itself. And here are the X-ray photons coming out in all directions, very evenly. So, you will encounter the anode material according to its path. A small part inside the anode material will experience attenuation to a small extent, so the transmitted photons here will be large, while a larger part of the anode will experience transmission to a lesser degree, and so on. For example, you see that the transmitted photons here are few because the X-ray photons travel a long distance inside the anode, which gives me an equal distribution or a homogeneous distribution in the intensity of the X-ray. So you have lost intensity in the lower area and higher intensity in the upper area. This is the region of the cathode and anode that I was talking about earlier.
But the topics where there are higher subjects than the second topics that have higher subjects, because I am doing the hardening resistance. This is a very beautiful segment, Dr. Hani. May God bless you. Mashallah. A good study session.
This is a point which is called the mean energy. That's why I tell you there is a difference between intensity. Intensity is not just about the number, it's about the number and energy. Number and energy, right? But when we talk about the average energy, the mean energy, Dr. Hani told me what now? Dr. Islam, the photonadi, is moving and is in a state. In the anode, this will remove the low energy. Once the low energy is removed, I have the part that passed through. For example, if I had X-ray photons that were emitted in the area near the anode, which were between 10 kilo electron volts to 100, and I removed from 10 to 30, then my average, instead of being 50, became 75 or more. So the number is just higher than the initial average, right, Dr. Hani? In contrast, what is moving towards the cathode has a high intensity. Its number in energy is high, but its average energy is lower as average energy. Average energy means there is a difference between the concept of the spectrum. When we said that the peak is exactly this point, yes, this is it. But did this solve the problem that I reduced the different average energy? It still didn't reach the homogeneity under the image or something like that, right? You are changing the mean energy, correct? But the intensity itself is important. Why is it important? Because you need a large number of photons to create interaction. For example, you might find at your cathode 120% intensity, 120% efficiency or intensity, and you will find at the anode 70%. The difference in intensity is very large. The difference in intensity is very significant. So even if the intensity is high, your mean energy did not solve the problem. It did not compensate for the issue because you are still talking about energy. You are talking about penetration. But right now, for example, if there aren't enough number of photons to create interaction, it will create noise in the image. This means that the image you will receive lacks enough interaction between the X-ray photons produced from the anode and the organ itself. That's why you choose a lower thickness to ensure interaction, so that the number of photons interacting with you is suitable for the thickness of that organ. Here is the X-ray origin or the focus point area where the interaction occurs. The X-ray will appear in different colors, and it will tell you that the distance traveled by the path length is, for example, at the anode direction, and this is at the cathode direction. This side is towards the cathode, and this side is towards the anode. So, the path length from the anode direction is large, and this is towards the anode. Therefore, the path length in the anode direction is significant. As Dr. Hani was saying, attenuation occurs, which is a process that reduces the intensity of the signal or wave in this particular part when compared to the direction of the cathode. Now, if I increase the anode angle, what effect will that have? If I increase the anode angle, it could potentially alter the distribution of intensity, leading to changes in the overall behavior of the system. This adjustment might affect how the signal propagates through the medium, possibly enhancing or diminishing certain characteristics. Maximization occurs with a small anode angle. This principle is vital in various fields, especially where precision is crucial. For instance, in medical imaging, a small anode angle enhances image clarity, aiding accurate diagnosis. Similarly, in industrial radiography, it improves the detection of material flaws. Understanding when to use a small anode angle is key to achieving optimal results in these technical areas. When do I need a small anode angle? If I want significant comments in mammography, I have to clear the chest area thoroughly to ensure accurate results, and the cathode, which plays a crucial role in the imaging process, for me turns into an essential component of the procedure.